Yes, class. Am I audible? Astha, Mariam, Shriyansh, Priyadarshini, Razan.
Yes, ma'am.
All right. Fine. So in the last class, we had completed with Biot Savart law. We had seen what was the direction also. The direction we had completed. So just let us just quickly revise it once. What was the direction for Biot Savart law? Now see, Biot Savart law was what? Biot Savart law said that magnetic field is directly proportional to certain things. Firstly, current that is flowing across the conductor, DL. DL is what? It's the current element. Current element means small section of the wire through which the current is flowing. Then sine theta, angle is made between what? Angle is made between the position vector, that is the separation of the point of calculation of the magnetic field to the wire, that is the theta, and between the current element. And r square is what? R square is the separation, position vector we call it. So B is equal to mu naught I dl sine theta divided by 4 pi r square. This is what? This is Biot-Savart's law, major statement. Here the constant term is mu naught by 4 pi, which can be written as 10 to the power minus 7, or you can write mu naught as 4 pi into 10 to the power minus 7. Now, main thing is of the direction. Let's just quickly revise direction. See, direction is what? If you have a wire with you, if you hold a wire, just let's quickly revise. Two methods we had discussed for the direction. First method said what? First method said that you just place your thumb along the direction of current. For example, class, pay attention to example 1, point A. This. Example 1, point A. This one. Example 1, point A. Here if you keep your thumb in the direction of current, see, current is flowing upwards. If you keep your thumb in the direction of current, this will be the direction. Try it. All of you try it at your home also, from wherever you are attending the class, right? And then curvature at A point. So at A point, fingers are curling out of the page. Which page you have to make all the references. This is the flow of current at point A. This is point A. Current is flowing towards me, out of the page. So we call this as outwards. Similarly, if you want to calculate it for point B, we'll have the thumb in the direction of current. Point B is located here. So thumb is pointing towards the screen, into the screen. So that will make it inwards. Like this was the first method to do. Second method was much easier, and I would not suggest any method because both the methods will give you the same answer. I myself prefer the second method. Second method says that you keep your fingers in the direction of current. This was the method till we had stopped in the last class. If you keep your fingers in the direction of current, earlier what we used to do, for the same example 1A, for this, what did we do? We kept our thumb in the direction of current, and curvature of finger gave us the direction of magnetic field. If this was the case, this showed that fingers are pointing towards me. It means what? They are out of the screen. If this is my screen, here fingers are moving away from the screen. That shows outward. Now, I'll keep my hand in the direction of current. So current is flowing upwards. I can keep my fingers like this, like this, like this, like this. Any possible way I can keep it. But out of this, which way should I choose? I have to choose such a position where I can curl the fingers towards the point of calculation. So for example, my point A is located here. If the point A is located here, this is the direction of current. Now, if I keep my fingers like this, I won't be able to curl it like this. Obviously, I won't be able to curl my hand like this. Even if I keep it like this, at point A, I won't be able to curl it back. But if I keep my fingers like this, this is point A. Now, if I curl my fingers towards the point, where is the thumb pointing? Thumb is pointing again away from the screen, out of the screen, that is outwards. You got the answer with both the methods. Method 1, point B. This one. Point B. Here you will have your thumb, and Class, remember you have to use only your right hand, because it happens you are right-handed. The dominant side is right, so you are in a habit to write with your right hand, and as soon as the question comes for solving in magnetics, you people use your left hand because it is freely available. So just be alert and careful whenever you are solving the directions. Be aware at least that you're taking your right hand, you're using your right hand for the solving of any of the direction of the problem. Because as I've told you, there are so many rules available. There are rules regarding and related to the left hand also. But if you understand and study both of these, no, ultimately you will get confused. When to use left one, when to use right one. Right one is pointing and giving this, left one is giving opposite, and at the end you'll be getting exactly the opposite answer. If answer is inwards, you'll be getting outwards. Right, see, if I do it with my left hand, this is point A. If I do it with my left hand, thumb is pointing where? Thumb is pointing into the screen. While what was the answer using my right hand? Outwards. So exactly opposite answers we're getting. So just be careful that you use your right hand. Even who are left-handed people, use your right hand, because we'll be just using the right hand rule for everything. We'll be just modifying it the way we had it right now. One gave this, one gave this, like this we'll be modifying. For circular also we'll modify it. All right, class. So this way we have the direction. So for the first, just B part, let's revise. Last thing, then we'll move on to one numerical from Biot law. Direction of current at point B, it is giving. Fingers are curling where? Fingers are curling into the page. Using the second method. This is point B. Point B is here right now. Look, I'm just looking at the screen and I'm solving this. When I curl it, when I'll curl the fingers towards the point, thumb is pointing. See, it's pointing towards you people. It means what? Into the screen or page. So that is into the page. Even if you do it on your notebooks, you can write it in your notebooks and then try all these methods like this. Fine. In the exam also, you have to do all this. So this was a quick revision of what we had studied yesterday. Any doubts from the last class? For the new students also, if you have not understood anything, just ask me. Just let me know from whichever topic you have not understood. This is a simple direct question based on your Biot law, and it's a question from your NCRT only. And this question has directly come in your board exams, not only even in your board exams, in your NEET entrances as well, NEET and JEE entrances as well. Just with a modification. In 12th board examination, values were also not changed. But in case of your entrance examination, the values got changed. So here, see, current, I'll tell you what it is actually. This is the current element on the x-axis. This is a point P given at the y-axis. This becomes your radius vector. Right, class? At point P, you have to find out the magnetic field the way you have been doing it, right? This is a wire, point P is this. So everything is just given like this. Here, this is your wire, point P is right now. You have to apply the rules exactly the way you have studied. Not if it is something is valid for this something, then that same thing can be valid like this also. So anything can be valid like this also. So you will get the different directions in different directions. So this is what? This is radius vector that is given to you. Current element, that small portion that has been cut, it's 0.001 meter. Current that is flowing is 10 amperes. I think this much data is sufficient. Put into the Biot law and see what's the answer you're getting. And nobody will answer without direction. See, class, because magnetic field is a vector quantity. So for the understanding of vector quantities, you need to have the directions associated along with it. So try, take 2 minutes, take 2 to 3 minutes, and we'll discuss. It's an easy question. Honestly, it's an easy question. Values are also very easy. Just try it. Then we'll discuss.
ما اقدر اجاوب شو اسمه شهر شهرين كده واحد المدرسه. والله كثير. شوف الاخبار ترى ما ينفع زي كذا.
Abdullah, your mic has turned on by mistake.
يس
Ma'am, one doubt.
Yes.
Ma'am, in this question, we have to use the scalar form of the formula, right?
You have to use the normal scalar form. B is equal to mu naught ideal sine theta divided by 4 pi r square. That you have to use. For the direction, those two rules that you have to do that we have discussed it right now. Okay, so you people are getting answer. Okay, Liana, fine. Priya, yes, Priya, your magnitude is right. Priya, try the value, that direction also, write the direction. Your magnitude is perfect. Astha, I think slight error is there in the power of 10. You're almost near the answer. Just check the value once again. Last 1 minute class and we'll discuss. Yes, Astha. Now it's correct. Minus or plus? The power, Astha. Yes, that's correct. Priya Darshini and Astha, both of you try the direction as well. See, point is given. Direction of flow of current is also pointing towards the positive x-axis. Apply any of the methods. Yes, answer. Correct answer. So you can even answer in terms of I cap, J cap also if you wish. Because right now you're doing a single question. So here there is no requirement of other properties or other quantity because you will just get one single magnetic field. When after, when we'll study all the different shapes and sizes and then we'll combine and find the resultant answer. So what will be happening? You'll be having a semicircular connected to a wire, to a straight wire which is connected to a semicircular arc. Like this, different shapes will be given. That way only question come. That time you may have difficulty because if you do not write it in terms of unit vector, then it becomes very difficult to solve. How will you add right plus up? but you can add I cap plus J cap. You know how the the techniques to solve it. So all of you, it's better right now. It's fine. It's fine. You can answer in terms of outwards, inwards, left, right. That's fine. But when you have a collection, when you have to find out more than one single magnetic field, try to write it in terms of unit vectors. Now, class. See, formula of Biot-Savart's law is what? Mu naught I dl sine theta divided by 4 pi r square. So mu naught by 4 pi is what? Mu naught by 4 pi, or even you can write mu naught as 4 pi into 10 to the power minus 7. So mu naught by 4 pi, this constant is 10 to the power minus 7. Fine, class. I, that is the current that is flowing through this conductor. Current is mentioned to you as 10 amperes. So this becomes into 10. So mu naught by 4 pi is 10 to the power minus 7. Current is 10 amperes. DL is what? DL is the current element, small section that has been cut through the wire. That is 0.001. I can write it as 10 to the power minus 3 as well. So this becomes 10 to the power minus 3. And here what I have, sine theta. See, class, the angle between the DL and the radius vector. Current element, this is taken as theta, and here it is 90 degree. So from here you already know that sine 90 degree is 1. So no problem of the angle that is present. Divided by 4 pi had already been considered under mu naught, so that we could write 10 to the power minus 7 and combine it. R square, R is given 10. That becomes 10 into 10. So 110 got cancelled. This becomes 10 to the power minus 10 into 10 to the power minus 1. That is 10 to the power minus 11. 10 to the power minus 11 Tesla. Now the complete answer. This is still not perfect. If you write only this much in your exam, it depends on the examiner, how much mark the examiner can reduce. Some marks will definitely get reduced for not writing the direction, but you do not know how much marks the examiner can reduce, because it can happen sometimes. No, it happens in the marking scheme. The marking scheme that is written within that is presided within the examiner. There are certain values and marks for every step. For writing the formula, half marks. For writing this, so that happens. In that case, we tend to lose marks. Now here what is happening? Using our right hand, this is the right hand. Try to do it along there. Otherwise, I'll ask you all to open your cameras and show me. Fine, class, because without this direction, nothing will become easier for you. And whichever part you're not able to understand, stop me, interrupt me there. I have given all you so much liberty that you can at least interrupt me in between and ask whatever you have not understood. Right now, what is happening? Current is flowing towards the x-axis. So as I've told you, for myself, I prefer the second method. So here also, I'll be preferring the second method. What will happen this time? Current is flowing towards the positive x-axis. And point P is where? See, point P is situated somewhere here. Like this is the case given. On the y-axis, point P is given. And this is the direction of flow of current. Curling the fingers towards point. Point is here. Curl the fingers towards it. Where is the thumb leading? Thumb is leading out of the page. This is outwards. Outwards is which axis? That is your positive z axis. So you can write it in terms of k cap also. 10 to the power minus 11 k cap Tesla you write, that becomes clear that magnetic field is outwards. But for this question, you can write outwards as well. Clear, class?
Ma'am, doubt.
Yes, Shan.
Ma'am, if you use our thumb to like point the direction of charge.
Okay, using the first method, you're saying?
Yes, I have the habit of using that.
Okay, fine. You can use the first method. See, that time by that also answer will come the same. If you keep your thumb in any direction, this will be it. Now, point is where? Point is here somewhere. See, fingers you have to just focus at that point. Where are your fingers moving? That is the curvature of magnetic field. If this is the thumb that I've kept, here is the point. Fine. Now, if I curl my fingers, at this point, what is happening? Fingers are pointing towards me. Fingers are pointing away from the screen, out of the page. This is the page for me. You can write it in your notebook and also check. So what is happening? This is showing that fingers are pointing exactly at this point. What is occurring? See, even if you just keep it above the screen where I have written, by whichever device you're studying. See, thumb will be here. This is your right hand, right thumb pointing in the direction of current. At P point, curvature of finger is outwards. That will give you again K cap, you can write or outwards. Fine?
Yes, ma'am.
Okay, note it down first. Written class.
Yes, ma'am, done.
All right, fine. Now, see, we have certain applications of Biot, and this is important because this is the basic for your magnetics. You'll be having different shapes. See, this part has actually been deleted. Magnetic field due to straight wires, derivation has been deleted. But we'll see the formula. So as I was saying, in case of Biot-Savart's law, what happened? The basic law you have studied. So if questions come, they come on this directly. R is given. Mainly you have to be careful with the direction. By direction, you can get confused. Now the first application includes, this has actually been classified into two groups. Straight wires classification, where it can be anything. It can be finite, It can be infinite. It can be semi-infinite and all this. This is the classification that is already done. And then magnetic field due to circular arc. Circular arc will also be having different. It will be having at the center of a circle, at the center of a semicircle. Then for a random circular arc which is subtending any random angle. Now what you have to remember, what all of you have to remember is just the formula, because see, it's a very rare chance that in your board exam this will be used. This will be used in combination, because most of the questions that are already present are in combination of this. From here you have to remember this and this, just the formula. Fine class, formula you can at least remember using and direction by your right hand thumb. Circular wire derivations you have to keep in. Derivation is just fixed on a certain pattern. One pattern derivation is fixed. So if you've understood once, you have to write it that only again, just a slight difference that we'll see where is the difference. So let's start with it. Let's see how much we are able to complete it today. Circular wise, I think derivations we should be able to complete it by today. So magnetic field due to straight wires, infinite and semi-infinite, you have to remember. Questions from infinite, semi-infinite can come individually. Coming of these are difficult in exams, in your board exams. In your entrances, you have to remember this. For your entrances perspective, whoever wants to appear for the entrance, you have to remember the formula. Now, magnetic field due to infinitely long wire. Infinite means anything that is extending to the infinity from a finite point. It is extending to the infinity. Now, the wires that we choose are extending from both the sides. Both the sides mean, if this is a wire, it is extending from plus infinity to minus infinity. This much long wire. But in most of the exams now, how the questions come, it will just simply give you wire, and sometimes these dotted lines are shown to show that it is an infinite long wire. If nothing is mentioned in your any kind of exams, by default, it is infinitely long wire. If it's a finite case or in any case, that you had to remember just the, that becomes specific whenever finite or any other thing is. By default is nothing is mentioned. Don't consider it as semi-infinite, finite, or anything. It is infinitely long. Otherwise, for semi-infinite cases, most of the times, no, pictures are and the diagrams are given for us. So using the figures, you can easily predict. So this is a wire. Wire is having current I flowing through it. This is the point of calculation, let's say, and this separation that we have taken, this is R. This is R that we have taken, and we have to find out the magnetic field at this point. So the formula of magnetic field for infinitely long wire. See, you have to remember the magnetic field due to infinitely long wire and semi-infinite. That's what I'm focusing on again and again. Infinitely and finitely. With a slight difference. Just a slight difference, you have to remember. Both the formulas become easier. Before I tell you the formula, no. Let me tell you what is a semi-infinite wire, so that you are able to understand and see the difference. Semi-infinite means a wire is there. Now this end is fixed at some point. This end is extending to infinity. One end is fixed, other end is extending. If the point lies near the finite end, like this is the position vector, this you call as semi-infinite. Fine class. So these two cases you have to remember. Now magnetic field for the infinite one. This is mu naught.
Ma'am.
Yes, James.
Ma'am, is the derivation for finite straight wire done in class?
No, finite derivation is not included. Now you don't even have to do that. Even these infinite and all these you don't have to do. That's what I was saying. No need to stress upon that so much. Just remember the formulas, because especially for the finite one, this question comes. For the finite perspective, you have to remember. So this is basically mu naught I divided by 4 pi r. Right? Now, magnetic field for semi-infinite becomes mu naught I divided by 2 pi r. Just a slight change in 2 and the value of 4. This is the difference. So what do we call this wire? We call this kind of wire as semi-infinite, because infinite from our end, half end is at infinity, half end is extending to infinity. So semi-infinite wire, and the point is lying near the finite end. That I'll write it down. Point is lying at the finite end. The point is lying at the finite end. So just note down these 2 points before we start with the circular one or any one. Just note down this one. Yes, Jens.
Ma'am, I just checked my class notebook, and for us semi-infinite wire, the formula is B is equal to phi naught by 4 pi I by A.
You not I by 4 pi. Yes. So what have I written?
Can you just scroll down once?
Okay, I've just okay. Yes. I have swapped it. Yes. This is right. This one is true. This one is true. I have written this one is true. This one is true. Because this will, especially this finite one, this will go along. C class. By mistake, I had written 2 over there and 4 over here. C class, this one formula, no, this will be used again in other derivations also. When we'll be doing Ampere circuital law and all, these will also be used. Then you will be having force due to a single wire. That time also this magnetic field will be used. And then you have a topic, force between two parallel conductors. That time also this topic will be used. So especially, yes, be careful with this. The way by mistake I had written, just make a correction if anybody has noted down. But this first case, that the magnetic field due to infinitely long wire, this will be used because force between two parallel long wires. Class, one more thing, if just long wire is also written, no, the term long, then also consider it as infinite. Long in we'll be having a solenoid and all these devices, toroid and all. So in solenoid also, when it is given, you have, if it is given long solenoid, so whenever anything is given long and nothing is mentioned apart from it, then do consider it as what? That it means it is extending from infinity. So if nothing is mentioned, do consider the term long. So both of them can be any of it. So from here, I think you have to note it down, no?
Ma'am,
Yes, Anushka.
ma'am, could you scroll up?
Yes. Yes. Written this much.
Yes, ma'am.
All right, let's solve a question on it. See, in this, no, three things are given. I'll just tell you what actually the question is. At least you can try it first yourself, then I'll discuss. It's a straight wire that is given here. This is a straight wire that is given. Current flowing is 10 amperes. First part says calculate the magnetic field at A point. So ignore other things that are present. A point is your point of calculation. 10 amperes is the current that is flowing through the wire. Separation between the point of calculation means the radius vector is basically 2 meters. And the wire is what? Wire is an infinite wire. This is the first case. So using the normal formula you will find the direction as well. Second part of this question involves magnetic field at C point. This is. Now C point is what? C point is semi-infinite. C point is semi-infinite. So semi-infinite means what? Here this end is extending. And this is what? This is semi-infinite. So when you're solving C, forget about A. Do not consider it. I have written it in a single question, no need to write it. So forget that timing. So C point is semi-infinite. This is the finite end where point is there. This is it. Then third is B point, and B point's location is exactly in front of you. So on this B point, you might have any difficulties, but at least A and C you can answer. So first and second part try. I'll tell you the answer of the third part, B part. Try it yourself. Take 2 minutes and we'll discuss. Whoever gets the answer, send your answers in the chat box.
OB is the infinite wire, right?
OB is the infinite wire. Yes, this wire is infinite. So for the first part, you will this will act as a completely infinite wire. For the second part, consider it as a semi-infinite wire. For the third one, point is given. Ask the direction also. Direction also. Liana, magnitude is right. Direction just specify. Radially means what? Either it can be left, up, downwards, inwards, outwards. You can write, or you can write in terms of the unit vectors I cap, j cap, k cap. Like this, you can write. Astha, check the direction again. Others also try. Only Liana and Astha have tried this question. Okay, so Rizan, Diana, Sashiansh, Priyadarshini. Okay, Liana, this is the answer for the second part. Fine. Magnitude is correct. And you have written, yes. Yes, Asta.
Ma'am, for the third one, B at B, which formula are we supposed to use?
Third one, I'll tell you. Third one is a different thing that we have not discussed yet. First,
Yes.
second part, you have tried, no? Both the parts you've tried.
Yes,
Let's discuss it. Yes, Liana is right. That's the right answer, Liana. I'll discuss it with the class as well. Third part is correct, Liana. See, class, for the first part, let's discuss just the first part. First part is what? Forget the C part, forget the B point, forget anything. For you, it's a long infinite wire. At point A, you are calculating the magnetic field. So what did we write? The formula of magnetic field for infinitely long wire is what? Mu naught I divided by 2 pi r. 2 pi r, 2 pi a, anything that you can write. Mu naught is written as 4 pi into 10 to the power minus 7. Current is 10. 2 pi is there, and radius position vector is also 2. So this becomes 4 pi. In the denominator, it's 4 pi. So 4 pi, this will get cancelled, and this comes out to be 10 to the power minus 6. Who all have answered it correctly? Priya Darshini has answered first part. Now see, direction, regarding the direction. Keep your right hand like this, along the direction of current. Now at A point you are calculating. So at A point, what will happen? At A point, just curl your finger. Thumb is pointing inwards into the page. So into the page, you can write it as inwards as well. You can write it in terms of K cap as well. You can write it as minus K cap. That will also go well. So I'll write it as inwards only. This much inwards. This much Tesla. Now answer for the second part. See, second part says magnetic field, which is semi-infinite wire. Fine. So semi-infinite wire, you just have mu naught I divided by 4 pi r. So see, class, this becomes 4 pi into 10 to the power minus 7. Current is 10 amperes. This is 4 pi. And again, position is what? Position vector, this is 2 meters at point C. So this becomes 2. So you get 5 into 10 to the power minus 7. This much distance. See, direction will still be the same. Current, your fingers along the current at point C. Even if you use the second rule, that way also. See here what is happening. Thumb is pointing inwards. If you use the first rule, first method, this is a thumb along the direction of current. Point A or point C, every point is along this only. Fingers are at this point where the fingers are pointing into the page. So this will also be inwards. So I think this was, yes. Priya, Darshini's, both the answers are correct. I think Shreyansh here that you've answered is for the second part, right? 5 into 10 to the power 7. All right. Now the answer for the third part. See, class, just remember one thing. If the point is lying on the axis, magnetic field will directly be 0. If the point is lying exactly on the axis of the conductor, your magnetic field will be 0. Here, B point is lying where? See, this is very important and it will ease your questions. Your answers, the answers that you will get, no. Maximum time the point will lie on the axis so that it will reduce one of the values and you will get the other terms. So point B is what happening. Point B is lying exactly on the axis of the conductor. So there is no magnetic field. Reason, can anyone tell the reason, by the way? Any idea? Magnetic field will be 0. Anyone?
Theta is 0, so
Yes.
maybe sine
Yes.
0.
Perfect. See, what was Biot's law? It was mu naught I dl sine theta divided by 4 pi r square. That was the whole formula. Here we are using the direct formula because we know it. Right now, in other cases, what happened? Angle between the DL and the position vector became 90 degree. So we could eliminate, and right now you don't have the derivation for this, so no need to go into the details of it. But when we are having it on the axis, the angle between the current element and the position vector. See, position vector is also this, and the current element is also in this direction only, if you take. So both are parallel to each other. So angle that becomes between the DL, angle that is formed between the current element, this becomes 0. So your sine 0 degree, this becomes 0. So ultimately you have the magnetic field also as here. So whenever she will be using these points as well. So wherever you will face, the point is lying on the axis. Axis can be anywhere, even if you have like this. This will be on the axis of it. Fine, magnetic field will be 0. So quickly note down the solution, then one more question we'll discuss before moving on to the circular part.
Ma'am,
Questions you have written. Yes, who is this? Liana. Yes, Liana.
ma'am, inwards means it will be negative k cap, right?
Negative k cap, minus k cap.
And outwards is positive.
Positive k cap. Remember the universal vectors will be used. See, z axis can be anywhere. If I wish, I can draw the z axis like this. This is the z axis for me. This becomes the x axis. So this one will be the y axis. If I wish, I can draw it. That is different thing. That is a specified case. A figure is given, you are solving accordingly. But the universal vectors which are actually present, the universal vectors which you study, the universal unit vectors, they are standardized, they are specified. For right, you have I cap, we use it for the directions. So for right, you have I cap, for left, you have minus I cap. For up, it's j cap, for downwards, it becomes minus j cap. Fine. Similarly, for outwards means away from the screen. That becomes k cap, and inwards become minus k cap. So here also you can write minus k cap. If it was a combined question, then you could add directly because both were in the same direction. Note it down. As you do, just text me done so that we can start one more question we'll discuss before moving on to the circular part. Others also have done.
Done, ma'am.
All right. So if all of you have completed, just have a look at this question. You have to find out the magnetic field at this point P. P point is mentioned. So these are unidentical conductors. Unidentical in the sense, what? Current is different between them. First one is having I, second one is having 2I. So note down the question. Just note down the question, then I'll discuss it. So these are completely long wires given. Now, see, this is the first question which has combination. Other figures are not involved, but at least combination of two wires, more than a single is there. Now see what will happen. Magnetic field due to the first one. Let's find it down. First wire is this, current is I. First wire is I given. Evan, can you just try the magnetic field? Can you just speak out the magnetic field at this point P due to this first wire? Evan. See, it will start with mu naught. Current, what should I write for this wire?
Ma'am, I
divided by, see, 2 pi will come, and separation
A.
2 pi a. Now the direction. Anushka, can you answer the direction? Outwards, inwards, k cap, j cap. Use your right hand and answer.
Ma'am, for the first wire?
For the first wire, just the first wire. Okay, fine. Yes,
It will
Anushka.
be into the plane.
It will be into the plane. Yes, correct. Inwards. So I'll write minus k cap for this. Perfect. This much Tesla is B1. Second wire. Razan, can you try second wire? Razan.
It will be mu naught I.
You not?
I.
See, second wire. What's the current, Razan, here?
2I.
2i. So it becomes mu naught 2i divided by 2 pi. And what's the separation?
A.
A. Exactly. The separation is A. And can you answer the direction?
Outwards.
It will be outwards. This is the, yes, it will be outwards. So I'll write k cap for this. K cap Tesla. This is fine, class. So that's why I was saying unit vectors will be helpful. Now, what's the answer? Answer is the resultant. B net will be what? B net will be the sum of all these. So B net magnetic field is what? This is sum of the first and the second magnetic field. So B1 is what? Mu naught I minus k cap divided by 2 pi a plus mu naught 2 mu naught I divided by 2 pi a k cap. Tesla. This much is it. You can do one more thing. You can take out these common mu naught I k cap divided by 2 pi a. You can write it as common. So what is left? From here minus 1 is left. From here plus 2 is left. So the ultimate answer will become mu naught I divided by 2 pi a k cap Tesla. This is the resultant magnitude. Fine, class. This is your answer.
Ma'am, what is inside the bracket?
This.
Yeah.
That is the common things that are left. See, from this bracket, what I have taken common? Mu naught I by 2 pi a k cap I have taken common. So minus 1 is left. See, if you multiply this, you will get this back. Plus from here, this 2 was extra. Mu naught I k cap divided by 2 pi a. So 2 was...
Okay, got it.
Note down the solution class. Then at least I think we can do one derivation. 1 or 2 derivations. So questions you have noted, I hope. If anyone wants to see the question, just text me. And just write done whenever you have completed writing. Anyone is writing? Done? Others? Have you understood this or not?
Yes, ma'am, understood.
What about you, Mariam, Ryan, Abdullah? All have got this? Let's start with the circular one. Circular one has a derivation. Fine. So the first certain steps are fixed. Certain steps are fixed that will be repeated for all of the cases. Firstly, we'll find out the magnetic field at the center of a circle. Or it's better, I'll write circular coil. At the center of circular coil. Now class. Magnetic field at the center of circular coil I have to find out. So this is my circular coil. At this center I'm finding out the magnetic field. A circle is there. A complete circle is there, and at the center of the circle we have to find out the magnetic field. At the end you have to remember all the formulas also. So consider a small element dl of a wire. dl is a small element that we have considered. This will be the direction of current tangential to it. Now we are finding the magnetic field due to this dl. Let's say r is the radius of it. And r is what? This is the radius of the circle. So dB is equal to mu naught I dl cross r divided by 4 pi r cube. No need to even write this step. Write the simple Biot law that is available. See, if we are taking a very small section dl, so we'll get a very small magnetic field dB I dl sine theta divided by r square. Sorry, 4 pi r square. This is the magnetic field, formula of magnetic field. Now, angle between the dl current element and the radius vector, this will be 90 degrees. So sine will get eliminated from here. Now this is a very small dl we are finding. Do we have to find it now because of a small element dl, or we are calculating the magnetic field for the entire circle? So if I have dl, and if I'll add all these small dl's together, dl plus dl plus dl, I'll ultimately get the magnetic field for the whole circular coil. So a method to add all these infinitesimally small elements are only by one method, integration. So I'll integrate this. Mu naught I divided by 4 pi r square dl integration, and here I have sine 90 degrees. So sine 90 will become 1. Here I am left with mu naught I divided by 4 pi r square integration of dl. Now, can any one of you answer this? If I join all those small elements dl plus dl plus dl, what will I ultimately get?
L, ma'am.
L. L is what, Shians?
The length of
Length of the circle. Yes, exactly. So what's the length of circle? Priya, you were saying something? Priya Darshini?
Yeah, the circumference 4 pi r.
Circumference. That is, what's the circumference of the circle? 2 pi r. So exactly, right. So all of you are correct. If you add all these small elements, dl, 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 these are such small elements. But when you will combine, when you will integrate, you will get the length back. The way Shians has answered that dl integration is L. Integration of dt is what? T. So similarly, here also you will get L. But what L is here? Here L is the circumference of circle. So you have the value of dl right now. dl will become what? dl will become mu naught I divided by 4 pi r square. I have taken r as capital R, no the radius. Let me write capital R everywhere. So I have taken capital R. So here I should write capital. Just make it uniform because it will become confusing. Because when you'll do Ampere's circuital law, the way in Gauss law you have a Gaussian surface, then you will have an Amperian surface. And from the Amperian surface, you have to define one Amperian loop's radius and other your quantity's radius. So that time it can be confusing. So 4 pi r square. Integration of dl will give you 2 pi r. What is left? This 1 r got cancelled, pi got cancelled, and 2 in the denominator. Magnetic field at the center of a circular loop is mu naught I divided by 2r. This is for a single circular coil. If number of turns are variable, n number of turns are there, you know you are not aware of how many number of turns are there. Let's say n is the number of turns. So for a single turn, if it is mu naught I divided by 2r, for n number of turns, it becomes B is equal to n times mu naught I divided by 2r. This is the derivation for a circular coil. Direction, I think direction also I'll tell you. Direction, let's do direction afterwards. First note it down till here.
Ma'am, could you scroll a bit up? Ma'am, done.
Ma'am, do we have to mention the number of turns thing in exam?
Yes, yes. In the derivation, you have to mention. If in the derivation, if it comes, you have to mention. If it is in the question form and number of turns are not given, then you will directly use b is equal to mu naught I divided by 2r. In the exam, you will show if n number of turns are there. And also, class one thing. In your exams, when if it comes, prove or show the magnetic field for the circular coil at the center of it, because you'll have one more case at the axis of it that we'll do later. At the center of it, that time what you have to do, mention every term. Consider a wire, you have to at least specify all the terms. Consider a circular loop of radius r, like this, write it in this way. Consider a circular loop of radius r with current I flowing through it. Then say I have not drawn current here, no. See, here I had written these lines, but when you write it in the exam, write it. Consider a small element dl in the wire, then magnetic field due to the dl element is given by this. If you forget somehow, you are lacking your deficit of time and you have to write the derivation quickly. And then what do? Ultimately, when you've written no till here, write all the terms, extend. I means the current that is flowing through the wire. Capital R is the radius of the circle, like this. So written, class? All of you have written?
Yes, ma'am.
Yes, ma'am.
Done? So I'll stop here today because the circular wire, circular arc is also left, semicircle is left, derivation is same. So practice this derivation once. Tomorrow we'll discuss this. Semicircular and circular arc have a fixed pattern on this only. And then we'll discuss the directions along with the questions, that mixed questions from finite also and from here also. All these questions we'll discuss. So class, I'm stopping.